Hello AP Physics, this is Dr. Brinzi and this is lesson 9.1.2 and we're continuing our unit on heat and temperature. In this lesson we're going to be able to explain why it's a bad idea to build a bridge from a single piece of concrete. Now by looking at this objective you might be wondering, what in the world does this have to do with heat and temperature? But by the end of this lesson you actually understand quite clearly that temperature has something to do with why it's a bad idea to build a bridge from a single piece of concrete. So let's go ahead and get started to find out what that connection is. In our last lesson, lesson 9.1.1, we learned that temperature is related to the average kinetic energy of molecules within an ideal gas. And each of these molecules in a gas is free to move. It's not connected with or attracted to any of the other molecules. Nothing is keeping it from going in any direction whatsoever, except maybe a collision with a wall or a collision with another molecule. And that was what we needed to assume in order to come up with what the physical idea behind temperature is. Well, the problem with that is that molecules in solids and liquids aren't totally free to move like they are in a gas. You can think of a liquid as where the molecules are sort of connected, kind of connected, and then a solid, they are definitely like in some sort of definite shape, and they're definitely not free to move around like they would be in a gas. However, molecules in a solid or a liquid still have some freedom to move and to vibrate. And to give you an idea of how, I have a couple of analogies here. You can think of a solid like the molecules of a solid are kind of like people who have their arms locked together. Okay, they form a definite shape and they have a definite line to them. But you could imagine that maybe this guy over here who has his head down, he might be getting a little antsy, and he might decide, hey, I got to get moving at least a little bit, so he might decide to start rocking back and forth. Now, even though he's hooked up into this chain, he can definitely still rock back and forth and create a little bit of kinetic energy for himself. And if he gets more and more antsy, he could rock back a little bit more. And so could anybody else in the chain. So there is still some freedom to move and vibrate. Now, with a liquid, it gets more interesting because in a liquid is kind of like all these little dogs here going for a walk. All these little dogs have some freedom to move around. They're not connected. They're not hooking arms with one another. Like, say, this little doggy right here in the middle. This little doggy, if he or she wished, could actually move all the way over here if they wanted to. But we certainly know that this doggy has no freedom to actually move down all the way down the street and go in the opposite direction. So, in a sense, this doggy is connected with all the other little doggies here. But this doggy does have some freedom to move and some freedom to vibrate. And this doggy has more freedom to move in a liquid than these people do in a solid. And temperature does still have a way of characterizing the average kinetic energy of this motion or this vibration, but it's a more complex relationship, and it's way beyond the scope of this course. Now, what happens when something has zero kinetic energy? Like, what if we were to idealize like some solid that has absolutely no vibration in it? We have to have some sort of temperature scale that describes what a solid is when it has zero kinetic energy. And a guy named Lord Kelvin was able to create a temperature scale. And Lord Kelvin took the Celsius scale, which was commonly used by scientists back in the day. And the Celsius scale is based on the fact that water boils at standard air pressure at 100 degrees Celsius, and it freezes at 0 degrees Celsius. So it's kind of based on the standard of water boiling and freezing. Well, nobody knew how far you had to go down on the Celsius scale before you had zero kinetic energy left. Until Lord Kelvin came along, and he was a pretty brilliant mathematical physicist. So he used a lot of mathematics behind his physics, and he discovered that, well, when you get down to negative 273 degrees Celsius, I figured that that's when you have zero kinetic energy left. So why don't we actually create a temperature scale that has this number equal to zero? So we're just going to take this temperature scale and add 273 degrees to each number, and that will allow this number to be zero. But it also says in this temperature scale that water will freeze at 273 Kelvin and it will boil at 373 Kelvin. And the reason we call it kelvins is in honor of Lord Kelvin, who actually discovered what this absolute zero has to be, this absolute zero temperature. Now, one other thing that may be obvious but maybe not is that you can't get a temperature less than this. The reason you can't get a temperature less than this is because you can't get negative kinetic energy. Kinetic energy always has to be greater than or equal to zero. And if kinetic energy is zero right here, then you certainly can't get any temperature less than that. So that's why we call it absolute zero, is because you definitely can't go below that temperature. Now, one of the ways that temperature affects solids and liquids is what we call thermal expansion. So when you increase the temperature of a solid or a liquid, it turns out that you can actually observe that its length expands if the temperature increases, or if the temperature decreases, the object will actually contract. And there is a linear relationship between the amount of the change in an object's length and the change in temperature. And that relationship is given by this equation here. The change in length of an object is equal to a constant alpha times its original length times the change in temperature. And we call this alpha. It's called the coefficient of linear expansion. And for different materials, this coefficient is a different number. And certainly when we are working with thermal expansion, you're definitely going to get a list of coefficients of linear expansion for different materials. Not only does temperature increase the length of a solid or liquid, but it increases the volume of a solid or liquid as well. The amount that the volume increases is given by a different constant times its original volume times its change in temperature, so it looks very similar. Except this time we actually use a different constant beta, and we call beta the coefficient of volume expansion. So it works in a very similar way. So thermal expansion can actually be quite good. It can do some great things. Like, have you ever had like one of these jars that's like super tight and you can't untwist it? Well, Mom told you to maybe run it under some hot water and try again. Well, why does that work? It turns out that works because of thermal expansion. When you run this under hot water, you are actually increasing the circumference of this ring around the jar. And when you increase that circumference, it gets a little bit looser than the glass. And you're able to then exert enough torque to actually twist it off. It's also the reason that we can use thermometers to measure temperature. We have mercury in a long, thin cylinder. And when we subject that mercury to some hot water, that mercury's length will expand because it's in a long, thin cylinder, and we can use that expansion to actually measure the temperature of this liquid right here. By the way, a piece of trivia for you, especially when I was thinking about this, is that if you have, like say, a washer, like the washers that we used, and it has a hole in the middle, if this washer has an increase in temperature, you may think that what happens is that the material itself, of course, gets bigger. I don't even know if I have enough room to draw that it's bigger. Let me try here. Whoop. Okay, so that's, maybe not. Oh, God, let's try again. All right, so it gets bigger. And you might be thinking that because it's getting bigger, that it's also getting bigger inward. But that's actually not the case. It turns out that when you increase the temperature, not only does the outer radius of the washer expand, but the inner radius of the washer expands as well. So you actually create a bigger hole by raising the temperature of this washer. You actually make the hole bigger. You don't make the hole smaller. Now, sometimes, however, this thermal expansion can work against us. If we took a solid, like maybe a solid rod of metal like we used for our trebuchet project, and we clamped that thing down on both ends. Okay, we clamp it down so that it can't expand and it can't contract. Well, when we raise the temperature, this rod is going to want to expand. Let me actually draw a rod right up here. Okay. This rod is going to want to get longer if we raise the temperature, but since it's clamped down here, it can't do that. What happens as a result is that we have to, there has to be a strain on this clamp, or on this, not this clamp, excuse me. There has to be a strain that causes it to not expand any farther. And that strain has to come with some stress that actually keeps the rod pushed in. And that will actually prevent the rod from expanding. So there is a tensile stress or a compressive stress. Actually, I drew compressive stress, right? But it's the same principle. There is a tensile stress that has to be the opposite of the thermal expansion. Excuse me, I said tensile stress. I meant tensile strain. There has to be a tensile strain that counteracts this thermal strain so that the overall expansion of this rod is zero. Well, if that's true, and if we use the formula for thermal expansion, I'll just put it in a little bit different form. And if we use our stress-strain formula that we learned in unit number 6, you combine those together, you can actually figure out that the stress that's introduced into this material by thermal expansion is equal to the opposite of its Young modulus times its coefficient of linear expansion times its change in temperature. So by clamping this rod down on both ends, I could actually introduce thermal stress, which can be a bad thing. Thermal stress can lead to things failing. It can lead to buckling of railroad ties. Now, the thermal stress is pushing in the upward direction and the downward direction, so it's trying to compress this railroad tie, and what's happening as a result is that this railroad tie ends up buckling. It can't stand the compression anymore, so instead of being straight, it actually ends up starting to bend because it can't handle all of that stress under compression. So you can take a straight rod and you can actually apply a stress upward and downward, and if it can't stay in this state, it will actually do something called buckling. And that's why this railroad tie is really, really super curvy. And this actually is a big danger to railroads because you can actually have a derailment and people can get killed as a result of this. You can also, more commonly, you can also end up with potholes. Potholes are caused by thermal stress in the concrete. If you get a little crack in the concrete, water gets in there, it'll expand and contract as temperature rises and falls. That will cause the crack to get bigger, which causes more water to enter, and it becomes a catastrophe. Eventually, it'll totally give way, and you will end up with a nasty pothole. And that's why you will see road workers going around, and sometimes they'll just take tar and they will put tar over these cracks because that's where the water is getting in and causing this thermal stress. So civil and mechanical engineers have to account for thermal stress in their design processes. Now, a couple of very common ways that we see this, and this is my last slide, by the way, is have you ever wondered why electric wires actually hang down like this and they're not like pulled taut so that they, this is a straight line? Well, it turns out that that's due to thermal stress because this copper wire has a coefficient of linear expansion, so as it gets cold and as it gets warm, it's going to want to contract and expand, and if you leave it taut, that contraction, that expansion is going to cause, it's going to cause a force on the electric posts that are holding the wire up. So that's why the electric wires are allowed to hang. Another way that civil engineers account for thermal stress, it has to do with our objective for today. It's a bad idea to build a bridge out of a single piece of concrete because that single piece of concrete can undergo thermal stress. And if you're trying to clamp a bridge down on both ends, to keep it in the same place, then you can actually end up causing thermal stress. Now, the way that civil engineers relieve that, if you've ever actually driven over a bridge, you'll actually notice that every once in a while, especially for longer bridges, you will see these joints. And these joints are put in there specifically because they allow the pieces of concrete to expand and contract. You'll notice that these teeth aren't exactly tight next to one another. That is a gap that allows the bridge to expand and contract. And actually underneath each of these joints is actually a roller so that each of these pieces of concrete can roll back and forth as it expands and contracts. You may not have ever thought that this isn't, tightly bolted down, but it's actually not. It's allowed freedom to roll back and forth because of thermal expansion. All right, so now you know why it's a bad idea to build a bridge out of a single piece of concrete, and you understand now what that has to do with our unit, which is temperature and heat. We're going to actually use these formulas in class to kind of figure out how civil and mechanical engineers calculate thermal stress, how they calculate thermal expansion, and hopefully we'll have fun with it in class tomorrow, and I'll look forward to seeing you then. Bye.